be able to analyse a scramjet nozzle, we need to learn a little bit about the behaviour of compressible flows. In this unit, we're going to cover what it means for a flow to be compressible, when this occurs, and the different types of phenomena that occur in the various regimes of compressible flow. In the majority of introductory courses on fluid dynamics, and in most of your everyday experiences, you deal with fluids travelling much slower than the speed of sound. Such flows are incompressible. The density of the fluid, its mass per unit volume, changes by a negligible amount when the flow interacts with objects. For example, when I pour this water into the glass, the volume of the water doesn't change, and neither does its mass. So the density of the fluid is constant. When I throw this paper plane, the air moves slowly over it, and if we measured the density of the air flowing around the plane, it wouldn't vary from that in the rest of the room. We also didn't see any unusual phenomena as the plane was flying. However, when the speed of the flow becomes comparable to the speed of sound, the flow becomes compressible. Density changes become significant, and all sorts of interesting phenomena start to occur. For example, multiple vapor cones form around this aircraft flying close to the speed of sound, which we certainly didn't see around the paper plane. So why does an increase in the speed of a flow lead to compressibility? Basically, faster flows have more momentum, so when they encounter an object, a greater pressure rise is required to bring them to rest. The greater the pressure rise, the more the fluid is compressed. An analogy for this is a spring being compressed, the spring inside this plane, as we drop it. When the spring hits the floor at a flow speed, the spring's only slightly compressed. However, if the spring hits the floor very fast, it'll be highly compressed. The same holds true for gases. So how common is compressible flow? In liquids, it's very rare due to the enormous pressure rise required to increase the density by even a small amount. A pressure rise of 20 megapascals results in the density of water being increased by less than 1%. For example, the working pressure of these fire hoses is very high, up to 8 megapascals, and when the water exits the hose, it drops down to atmospheric pressure, which is almost 80 times lower. But this still isn't enough to cause a significant change in density. On the other hand, gas flows are fairly commonly compressible. If air is stored at more than double the pressure of the surrounding atmosphere, this pressure difference is sufficient to accelerate the flow to Mach 1 when the stored air is vented, causing a substantial change in density. So, compressible gas flows are quite common, but what are the consequences of this? First, let's look at it from an analysis point of view, as our eventual goal is to analyse a scramjet. For incompressible flow, the variables we need to solve for are the velocity v and the pressure p. To find these, we solve the equations of conservation of mass and momentum. For compressible flows, on the other hand, the density is now a variable, and so is the temperature T. To find these extra variables, we're going to require extra equations. These are typically conservation of energy and an equation of state. An additional consequence is that the classic form of Bernoulli's equation, introductory fluid dynamics student's best friend, no longer holds because it's derived by assuming the density is constant. The next question to answer is, when is a flow compressible? When do we have to worry about these extra equations? A very strong indicator of compressibility is the Mach number m. As you learned from David, this is the ratio of the flow speed to the sound speed. When the Mach number is less than 0.3, the flow is essentially incompressible. An example of a very large-scale incompressible flow, in which density variations are negligible, is shown here. This is the result of wind flowing around the Juan Fernandez Islands. The wake of the islands is unstable, causing what's known as a Kármán vortex street. The alternating sign vortices are easy to see due to the absence of the clouds in the vortex cores. For Mach numbers between 0.3 and 0.8, we have subsonic compressible flow, where density changes are appreciable, but shock waves don't form. The Bugatti Veyron edition pictured here has a top speed of 431 km per hour, giving it a Mach number of approximately 0.35, so compressibility effects will be important. Where the airflow stagnates against the front of the vehicle, the flow density will be significantly increased and the pressure will no longer be given by Bernoulli's equation. By the end of this section of the course, however, you'll be able to precisely calculate what the density and pressure are in reality. At Mach numbers between 0.8 and 1.2, flows are labelled as transonic. They are characterised by regions of subsonic and supersonic flow. In this image, the flow upstream of the airfoil is subsonic, but the front of the airfoil acts as a nozzle, which accelerates the flow past the sonic point. Shock waves then form that compress the flow and bring it back to a subsonic state. At higher Mach numbers, the flow is supersonic and is typically dominated by shocks and expansion waves, as in this image shown here, which is a visualization of the wave structure around a model of NASA's X-15 vehicle tested in a wind tunnel at Mach 3.5. Finally, beyond Mach 5, the flow becomes hypersonic. The shock waves become strong, resulting in high gas temperatures. Initially, this causes the individual molecules to begin to vibrate, which changes the gas properties. At higher Mach numbers still, chemical reactions become important, as does radiation. This image shows the shock tunnel test of the first scramjet to produce net thrust. It's at Mach 8. The shock waves are visible due to the air being hot enough to be luminous. Hopefully, you now have an understanding of when a flow is compressible and what compressible phenomena are likely to be important at different Mach numbers.